Right. So we were discussing the 3-qubit code yesterday, and we finished pretty much discussing various aspects of it. So let's quickly recap that the 3-qubit quantum error correcting code can correct for single qubit bit flip errors, right? Just give me a second. I will just pause the. Okay, I hope everyone's able to hear me. Yeah. All right. So we went through all the various steps of it, right? We went through the encoding, the decoding. So the way we do this is to say that the noise acts on the encoded qubits, and then comes the error detection, for which you need the so-called syndrome measurements. You need to get these classical syndrome bits which tell you what errors occurred, and then you error correct, right? And then you decode, where the decoding I'm now using in the sense that it's simply the inverse of the encoding, right? Remember that the encoding takes your information from a single qubit space to what is called a code space, right? So the decoding has to bring you back from the code space to the single qubit space. That's what it does. And I just want to point out that going forward, this set or this pair of steps, right, which involves error detection and error correction, will often be bunched together to be called a recovery operation. Okay. So this is often just called a recovery. And this can be thought of as a map, as we will see subsequently. So I will denote this by some R. The noise itself is some CPTP map. Let me call it N. The recovery also can be thought of as a CPTP map. So together, we have these three different objects. The code space C, you have the noise channel, which is a CPTP map. The recovery can also be thought of as a map, and we'll discuss this a bit more in detail. But for now, just accept my word, or maybe you can already see that the recovery after all is what? It's some measurement and it's some unitary transformation. So indeed, all of this falls under the category of CPTP maps, as we already discussed. So the recovery also is like a CPTP map. And this is what characterizes the error correction procedure. Now, what we discussed with the 3-qubit code was very much inspired by a classical error correcting code, right? So then you may ask, what was new, right? Yes, you did go to a code space, you had to cleverly design the encoding, you had to cleverly design the measurements, etc. But really, is that all there is to quantum error correction? Well, this is just the beginning, right? Because this was a particular noise model, namely bit flip errors. And I began the whole story by telling you that you have this whole class of completely positive trace preserving maps, it's a continuous parameter family, etc. Right? So then what about any other noise channel? How does it work? Do you have to go about designing specific error correcting codes for every noise? Do they exist? How does one go about doing it? Is there a method to this madness? Or do we have so-called general purpose error correcting codes which can correct for arbitrary errors? So over the next few lectures, we will try to address all of these questions, right? So the very next thing to do, which you can do once you've understood the 3-qubit bit flip code, is to think about quantum error correction for the phase flip channel, right? Because it seems kind of intuitive that this should follow the same approach. After all, what is the phase flip, right? So let me say, actually, I might start using N for noise, okay? I know I've been using E as a kind of, as a way to, or epsilon to denote the CPTP map, but N also denotes the same thing. So I will say N is the phase flip channel, right? So this is the, so let me write it like this. So you have the phase flip channel. N, which has these two cross operators. One is again the identity, and then you have the Z operator, right? So how can one design an error correcting code for this? Any ideas? Because you see, right, the between bit flip and phase flip, all that is different is the noise operator. This is also a noise channel with just two cross operators, has the same structure as the bit flip noise, except that X is replaced by Z. So can one design a repetition code for this? So first of all, it should be clear that the same repetition code that we did for the bit flip noise, will this work? So let's look at an arbitrary state in the code space. It will have this form, okay? And then you have all possible errors, as you know. So if I do a 3-qubit repetition code for phase flip noise, and I stick to the same code that I had for bit flip noise, then what happens? Suppose I have the Z error on the first qubit, right? So yeah, let me just get some more space. So once again, the set of possible errors are just identity with 1 minus p to the 3 halves. This is identity tensor 3. And then you have square root p and 1 minus p. Z tensor, I, and the variations of this. Basically, the Z error acting on each of the 3 different qubits. And then you have all the higher order errors, right? So now what happens to this? So what happens to this code, this state in the code space? So what I'm trying to ask is whether the same bit flip code, so this is the 3-qubit bit flip code, can it work for phase flips, right? And then what happens under these different errors? I'm just going to look at the single flip errors, right? So these are of the form this. And then what do you see? What happens to the state under these 3 errors? Yes?
Beta will have an negative sign.
And good. And that's the same for all of them, right?
Yeah.
So the key point is that I get the same state right? So if I think in terms of what's happening to the code space, you will realize that the code space is essentially getting mapped to itself under the action of different errors, right? Including the no error case. So now what? How does one go about detecting any of this, right? So this is the same state under different errors. Which means not possible to distinguish them, not possible to detect, and hence not possible to correct, right? Even the single bit phase flip errors. Okay, so clearly the 3-qubit bit flip code doesn't work. Any ideas? The question to ask is, what was the underlying logic for the bit flip code to work? The error was of the X type, but the states, the code words, were eigenstates of Z operators, right? So let us try to apply the same logic here. Now the error is of Z type, okay? And clearly, if I simply pick eigenstates of Z, it's not going to work. because these are all states that are left invariant by different Z errors, right? They are eigenstates of Z. They continue to be eigenstates of Z. So what kind of repetition code can we do? Yes? No ideas, huh? So we need a different QEC code, and I'm going to show you a 3-qubit repetition code for phase flip errors. And the point is that your logical zero should no longer just be 3 zeros, but it should actually be plus, plus, plus. This becomes the logical zero, and obviously minus, minus, minus becomes the logical 1, right? So how does this work? I will just go over the argument very quickly, and I will leave it to the assignment for you to work this out, because the analysis is exactly the same as the bit flip code. So first of all, is it possible? So what happens? An arbitrary alpha 0 plus beta 1 will now go to alpha plus 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 beta minus minus minus, right? And now what happens under the action of different errors? So now if I have a Z error on the first qubit, what happens? What is the action of Z on plus? It takes me to minus, and Z on minus takes me to plus. So this gives me alpha minus plus 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 beta plus minus minus. So you see, you've essentially replaced your zeros and ones with the superposition states plus and minus. And then what you have is essentially like a bit flip noise, except in a rotated basis. What is phase flip? It is bit flip in a rotated basis, right? So now if I do IZI, you see that I have alpha plus minus plus plus beta minus plus minus. And then IIZ becomes alpha plus plus minus plus beta minus minus plus. And now you see these are states which are all mutually orthogonal, right? Exactly what happened with the bit flip code. So now I can once again draw the same picture where the code space is getting mapped to non-overlapping subspaces. So I will just write this in words. I've drawn this picture multiple times now. So the code space C, which is now the span of plus, 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 and minus, minus, minus. Notice that this is very different from the span of 0, 0, 0 and 1, 1, 1, because each of these states is a superposition of 0 and 1. So this, when I expand in the 0, 1 basis, is going to have all possible terms in this. Similarly, this is going to have all possible states of the computational basis, right? I hope you understand that this is very different from just picking two states in the computational basis like 0, 0, 0, 1, 1, 1 and making a code space with that, right? This is a very different code space. It is a span of these two states, and this gets mapped to non-overlapping subspaces under the action of the different single qubit operators, noise operators, right? So by now it should be clear that the best one can do with doing this kind of repetition code is possibly only to correct for single qubit errors, right? You run out of room in the code space to be able to correct for 2-qubit or higher errors, right? So it gets mapped to non-overlapping subspaces under the action of the identity tensor 3 operator and the 3 single qubit error operators. So what we now have is a set of correctable errors for phase flip noise on this code, right? So I hope the idea is clear that this is simply a bit flip in the plus minus basis, right? The action of the phase noise is like a bit flip, except it's in the plus minus basis. And so you fix it by encoding into a repetition code, which instead of 0000111, now encodes into plus 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 minus minus minus. So let me show you some circuits for this. So how do we do the circuits and what is the basis in which we are going to measure? Both of these are important questions because, sorry. So what is the circuit for this? So clearly there has to be one additional gate compared to what we did last time for the encoding circuit. And what is this additional gate that you need to get to this plus minus basis?
Hadamard.
Indeed, you need the Hadamard. So once again, you have the C naughts, the 2 C naughts. And then you need these Hadamards. And that's it. You can check that this maps alpha 0 beta 1 to alpha plus 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 beta minus minus minus. What about the decoding? So please check this, okay? And what about the decoding? Rather, what about, let me say, error detection and correction? Let me just focus on error detection because correction becomes clear, right? Correction, you know that you simply have to apply a single qubit Z gate wherever, depending on what your syndromes tell you. So what is the error detection circuit? In particular, what is the syndrome measurement? So what do you have to do now in order to detect the phase flip error? So once again, you have your encoded qubit, and then you have this. So let me just draw this. So you have your. So these are the so-called noisy encoded qubits. You have encoded 1 in 3, right? And okay, so let's first look at this here and this and figure out what measurement we need to do. So I told you that these states are orthogonal. Okay, these 3 states you get from the single qubit Z errors, they are orthogonal. But what measurement is going to detect them? So once again, there are 2 ways of looking at it. If you remember yesterday, we discussed the 3-qubit code. We said that essentially you have to write down these projectors onto these different subspaces into which these errors are mapping you to. So I can once again write those projectors. And suppose I'm directly measuring these states, the noisy versions of the encoded states, then the measurement seems to be in the Z basis, right? However, if I want to take out these ancillas and understand.
Excuse me.
Yeah.
Z basis or X basis?
Yeah, exactly. That's what I'm coming to. So you're right, indeed, that the measurement in this case will have to be done in the X basis, right? Why did you say X basis?
I mean, by the same logic, like 3, because like we changed 3-bit code from 00 to plus plus plus. I mean, I want to check where exactly phase error has occurred, right? That would be easy to measure in the basis of X.
Yeah, so the logic is identical. So the point is you again have to do this pairwise parity measurement, right? It's the same thing. You have to do a pairwise parity check. Except now the parity check is whether you have a plus plus minus minus or whether you have a plus minus kind of combination, right? So if I were to do an X measurement, if I were to measure X1, X2, right? And remember, plus and minus are indeed the eigenstates of the X operator. They are not eigenstates of the Z operator. They are eigenstates of the X operator. So this is like a parity check in the X basis, right? So if I want to still call the syndrome measurements as 0 and 1, maybe it's less confusing to call them plus minus in this case. So let me first draw a syndrome table for this, and then I will show you how the circuit works. Okay. So let me write down a syndrome table. And the measurements that one has to do are, so now I'm going to put some indices here. So I'm going to say x1, x2, okay? This is the same as saying x tensor I. There are 3 qubits and I'm going to measure x on the first 2 qubits. So I'm going to call this as x1, x2, and then there is x2, x3, right? Which is the same as saying identity tensor x. These are the 2 Hermitian operators that I'm going to measure. The analogous thing in the bit flip code, the measurements are Z1, Z2, which is the same as saying Z tensor I, and Z2, Z3, which is the same as saying I tensor Z. Okay. I hope this notation is clear because now we are going to move very soon to a 9 qubit code. Okay. And I'll no longer keep writing these kind of tensor products. I'll simply put indices like this to denote which qubit is being measured and what is the measurement that is being done. Right. Okay. So let's write down first the syndrome table based on these non-overlapping subspaces. So I have okay, so for that I have to complete the circuit now. Wait, let me do that. All right, so I need my 2 ancilla qubits, right? And there is going to be some measurement at the end of the ancilla qubits. So let me just put some 2 measurement boxes for now. I'm still not telling you how this is happening because this is a slightly different circuit from what we did earlier. The same C naughts are going to be used, but they're going to be used in a different way, as you will see. So let me call these as S1 and S2, the same syndrome bits. So these are the classical syndrome bits. Okay. And I will again denote this as 0 and 1. Okay. So if you wish to make it less complicated, let me say that these are now X basis measurements. So let me say this is an X basis measurement. So I will call the syndrome as plus and minus, okay? Just so that we can immediately identify the error. So there is S1, S2, and then there is the diagnosis, and then there is the correction, right? It's the same kind of idea, the syndrome table, except that now you will have plus plus, plus minus, minus plus, minus minus, right? These are the 4 possible outcomes. So I will also tell you that these ancillas will be both prepared in the plus state. This is of course easy to do. You start with a 0 and then you subject it to a Hadamard and you get a plus, right? So instead of initializing your ancillas just at 0, we're going to initialize them to plus, right? And we are going to measure in the X basis. How we extract the syndrome, we will see. But this is the kind of table that we expect to have. that if you have both plus, right, that means there was no flip of any form. There was no phase flip. Okay. So then there is no error. Okay. This would be the identity. The correction is simply the identity operator. Plus minus means there was an error in only in the second pair, which means that the error is in the third qubit. So this is identity 1, identity 2, Z3. Correction is simply Z3. This means Z1, identity 2, identity 3. So the correction is Z1. Minus minus means the error must have occurred in the middle qubit. So that means that this was the error operator IZI, identity 1, Z2, identity 3. So the correction is Z2. Okay. So this is what we would like to have, right? Ideally, if I were to just, I'm just changing my zeros and ones to plus and minus everywhere, literally. And I'm changing all my x's to Z, right? That's the logic that I'm following. But in practice, the circuit, it turns out, is a tad bit different because, well, the Z and X behave in slightly different ways. So I'm going to draw the circuit first and then we'll see how that works. So earlier we just had these C naughts coming from the with the encoded qubits as the control and this as the target. But you will see that what you need to do now is the other way around. You need to now have C naughts with the ancilla as the control and the encoded qubit as the target. So this is the first pair. Okay. And for the second ancilla, you now have Z2 and Z3. So let's just do a little bit of analysis to see why this works and how is it that this leaves this state unaffected. Okay. Have you guys seen a circuit like this before? So I don't know if you recall when we analyzed the C naught, we analyzed it in different ways and then we analyzed it, the difference between the C naught in the 0-1 basis and the plus minus basis. And I think we saw that if you do the C naught in the plus minus basis, it essentially becomes like a flipped C naught, right? Where the control and the role of the control and the target are flipped. I hope you guys recall that. That is precisely the logic of this. So let's analyze this circuit and make sure that it works. So let's just look at this. So suppose I apply the C naught on, let's say, plus tensor some ket x, okay, where this ket x is an eigenstate of the x operator. Which means it's either plus or minus, right? So now the control is here and the target is here. And this is exactly what is happening in this circuit where my data qubit or the encoded qubit is now like the ket x, right? It is an eigenstate of the x operator. It's either plus or minus. That's what the encoded qubits are, right? If there's no noise, then they remain plus or minus as they were encoded. If there's noise, the plus flips to a minus, the minus flips to a plus. So whatever it is, it's an eigenstate of x. And the ancilla is in the plus state. And this is the C naught action, right? So this is what I'm analyzing here, right? And then you will see that what it does is, so this is like this, it's 0x plus 1x by root 2. With the C naught acting on this, right? And then what does the C naught do? It does nothing to the first one. The second one gets acted by an X gate, right? So the C naught is what? It's identity tensor well, I'm sorry, it's not identity, right? It's 0, 0 plus identity, oops, 0, 0 tensor identity plus 1, 1 tensor x. Sorry about that. So this is what the C naught is. If I expand it in this basis, and then you have the state here. So this tells me that nothing happens to the first state. The second state picks up a minus sign depending on which eigenstate x is, whether it's a plus eigenstate or a minus 1 eigenstate of the x operator, right? So you see this ends up as 0 plus minus 1 to the x 1 tensor x. So there's a by root 2. So essentially, this is either plus plus or oops, minus minus. You see that? So if x were plus, then this remains plus, the control remains plus. You see the target is actually unaffected. Whatever it was, it remains the same. I could jolly well have replaced the target now by a superposition of eigenstates of the x operator, and the same action will go through. If the target was a minus 1 eigenstate, if it was a minus state, that minus gets dragged down to the phase of the control, right? So essentially, the point is that this operation is like doing an x measurement. So this is exactly the same as an x measurement of the target. Of course, I've not yet put in a measurement. The measurement comes. So remember now this is control and target, and this control is our ancilla bit. So we are only going to measure this. We are not going to measure the target, right? So if I measure the control in the x basis, so this I should measure in the x basis, right? Then whatever outcome I get is either plus or minus depending on what x was, right? So effectively, so what this classical bit value is this little x, which was the label for the target state. So the classical bit value tells me whether the target is a plus 1 eigenstate of the x operator or a minus 1 eigenstate of the x operator. And that's exactly what an x measurement of the target should do. And in this case, the first qubit is our target and the second qubit is the ancilla, which is the control, right? Is this idea clear? How the phase of the control actually gets dragged into the target, and the target changes phase depending on whether the control was a plus 1 eigenstate of the x operator or a minus 1 eigenstate of the x operator. Any questions? Okay, so this then is how we are going to achieve the syndrome measurement, right? Because we need to measure in the x basis, and a measurement in the x basis will tell us whether pairs of qubits have the same relative sign or not. That's what you're checking, right? Whether pairs of qubits, whether both of these are plus plus, or one of them has flipped to a minus, or both have flipped to a minus. And depending on that, depending on how pairs of qubits have changed, we are going to decide which of the errors occurred and correct accordingly. Okay. So of course I can replace this box which says x basis measurement. I can implement this if my architecture only has the ability to measure in the 0-1 basis. Then what I can do is put a Hadamard and then do a 0-1 measurement, right? So the x basis measurement can effectively be realized like this, just like how the encoding starting from a 0 simply requires a Hadamard to initialize the ancilla to the plus states. Okay, so this is the syndrome detection circuit or the error detection circuit, and then error correction is exactly like what we said. It's simply a Z, single qubit Z, depending on where the, depending on what the syndrome tells you. And then that's it. So we can do the same error analysis, performance analysis, etc. So same error analysis. As the bit flip code. And in fact, you will get the same error threshold which is p less than a half. Okay. Any questions on the phase flip error and phase flip code? Okay. So if there are no questions, then I will proceed to discussing the next thing, which is what happens if there's now a combination of bit flip and phase flip, right? Because it's not as if the qubits are going to be obliging to us and say that, okay, now I'm only going to have bit flip noise. So you just use your 3-qubit bit flip repetition code. I'm only going to have phase flip noise. So qubits will have arbitrary noise, right? So what about arbitrary noise? So can we essentially design what are called general purpose error correcting codes to protect against arbitrary single qubit noise? So a first step towards that would be to look at a code that can correct for bit and phase flip errors. Can one construct such a code which can independently correct for bit flip and phase flip? And this is indeed what the 9-qubit Shor code achieves. So this was so of course this is due to Peter Shor, the same Peter Shor who also designed the factoring algorithm, right? So, and you see, whatever ideas we need for the Shor code, we already have. Because the Shor code is what is called a concatenated code. It is a code that combines the bit flip and phase flip repetition codes. To correct for a single qubit bit flip, you need 3 qubits to execute this repetition code. To correct for a single qubit phase flip, you need 3 qubits to execute a repetition code. Now you want to be able to correct for bit flip and phase flip independently. Then it's what you need is essentially 3 times 3, 9 qubits, right? So that's where the 9 number comes from, right? So the rest of this lecture, I just want to discuss the 9-qubit code. I will show you what the code words look like, and I just want to discuss the code, encoding circuit, etc. The error detection part will be very similar, the analysis, to what we have done now separately for the bit flip and the phase flip. There are some minor subtleties, and we'll discuss those. And then in the next lecture, what we'll do is to talk about a method to this, right? And whether we really need 9 qubits to protect against arbitrary single qubit noise. Is that like the magic number, or is there some smaller, can we design smaller error correcting codes? Okay, so what is the Shor code now? So I'm going to encode 1 qubit into 9. qubits, right? Which means I'm going from a single C2 to C2 tensor 9. You can think of the C2 tensor 9 as being broken up into a C2 tensor 3, that tensor 3. And this is what I mean by concatenation. So I'm building a structure on top of a structure. I already have a repetition structure for the 3-qubit bit flip code. I have a repetition structure for the 3-qubit phase flip code, and I'm going to build one on top of the other now, right? So this is what one means by concatenation, right? So let me just write down the code words now. What are the logical states? What is the logical 0 and the logical 1? So 0 is now going to get mapped to 0, 0, 0 plus 1, 1, 1 by root 2, whole thing, say tensor 3, right? Which means I have this structure, right? So this gets mapped to 0, 0, 0 minus 1, 1, 1, like this. So these are the two logical states. So let me write it like this. So 0 gets mapped to 0 logical, which is now a 9-qubit state of this form. And 1 gets mapped to 1 logical, which is another 9-qubit state of this form, right? So if we were to break it down and see how this concatenation actually works, then you will realize and now each qubit in this is encoded into a bit flip repetition code. Then this should get mapped to, the plus becomes 0, 0, 0 plus 1, 1, 1 over root 2, right? So this becomes this. So I hope you understand how this happens. Did we lose internet briefly or something?
Yes, ma'am.
Yes, ma'am.
Okay.
Yeah.
How much did we, I don't know.
From two layers, from two layers.
Okay, so I can just repeat that part once again, although it might have gotten recorded, I hope. So yeah, this is the concatenation part. I was just trying to explain the logic behind this, because if I just look at these 9-qubit states, they kind of look scary and it's not clear how one got these states. The point is that this first each set of 3 qubits is in a phase flip code first. So the phase flip code is the first layer, and this takes 1 qubit to 3, right? And so as we saw, the 0 goes to a plus plus plus, and the 1 goes to a minus minus minus, and that's why an alpha 0 plus beta 1 became alpha plus 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 beta minus minus minus, right? That's what the phase flip code was. And then every qubit of the phase flip code is now encoded in the second step into a bit flip code, right? This is the second step where each qubit of the phase flip code is encoded into a bit flip code. So each plus, right? How does plus look like in a 3-bit repetition code? It looks like 0, 0, 0 plus 1, 1, 1 over root, right? And similarly for minus, so you can see that the minus, minus, minus then becomes 0, 0, 0 minus 1, 1, 1 by root 2. And it's just that repeated 3 times across the remaining 6 qubits. So is this idea clear? I hope the code word structure is clear, right? So there are 2 layers to this. The first layer is a phase flip code, and the second layer is a bit flip code. On top of that, the encoding circuit also reflects that, okay? So one can draw the encoding circuit for this. And so now you have a single data qubit and 8 ancillary qubits, right? And whatever information was encoded in this single data qubit is somehow smeared across these 9 qubits in total, right? So if you think about it, I will first do the phase flip part, right? And the phase flip basically requires 2 C0s. And Hadamard's, right? So this is the phase flip circuit, right? But now I'm again tripling this. So 1 qubit went to 3, and now each of these qubits again is tripling, right? It's becoming 3 again. So I now take 2 more ancillas like this and just do the bit flip circuit, which is this. Right? You see now the second qubit itself becomes the control. What was originally the second qubit, this has become the control now for, it has become the fourth qubit in this code, and it has become the control for the next 2 qubits, the 5th and the 6th qubits. So this is what concatenation looks like. There's a kind of self-similarity to this, as you can see, 1 becoming 3 and 3 becoming 9. And today, people look at quantum error correcting codes, which are concatenated up to very high degrees, right? And this is the idea that is usually followed. And this is a very standard and useful technique now in quantum error correction to do concatenated codes. And you can see why. So that's it. So I have these 9 qubits now, and I will leave it to you to work out that indeed these 9 qubits are now in the superposition of the form alpha 0L plus beta 1L, right? Where you started out with the state alpha 0 plus beta 1, okay? The 0L and 1L are now these 2 9-qubit states with this interesting concatenated structure. So that's the encoding. What is the noise model now? the noise now acts on 9 qubits, right? And the idea was to see if so, as always, one has to look at noise channel and the set of correctable errors. So the noise channel now is twofold. There is the bit flip channel, there's bit flip noise, and there is phase flip noise. And the underlying assumption is that they act independently on the qubits, which means the same qubit could get independently affected by bit flip and phase flip noise, right? There is a certain probability for bit flip, there's a certain probability for phase flip, and a given qubit can independently get affected by one or both, right? And intuition again tells us that the set of correctable errors must be the set of single qubit errors, right? So let us look at the single qubit X errors, the single qubit Z errors, and see how this code handles all of that, right? So if I have the single qubit X errors, what happens? The zero logical state. So now remember that the single qubit errors act on any one of the 9 qubits. So I now have errors of the form. So this is why I said I'm going to start using number the qubits now, and you can take it that I will number them in sequence like this. So I will call this 1, 2, 3, 4, 5, 4, 5, 6, 7, 8, 9. Okay. This is how I'm going to number my qubits. So I'm going to say that you can now have errors of the form x1, x2, etc., x8, x9. You can have z1, z2, etc., z8, z9, where this tells me which is a location at which the error has happened. And of course, you have the identity. So all of this along with identity, right? Which is the no error case, and this is identity tensor 9. And you can put all the probabilities for this. You can even assume that the parameter P is the same, right? It's an interesting question. What happens if the parameter P is actually different for the bit flip and the phase flip? And now, there's some understanding that there could be certain architectures where bit flip is more common than phase flip. Actually, usually it's the other way around. The phase flip is more common than the bit flip. Because phase flip comes from a very intuitive physical model, underlying physical model. So then what do you do? So there are what are called biased noise codes and all that, but I guess that's an interesting direction for you to do your term, the presentation and term paper for this course towards the end. But for now, let's say that both noise occurs with the same probabilities P. It's IID, so it's identical and independent, right? Acts independently. Okay, so under these single qubit X errors, what happens to zero logical? And I'm going to just draw 3 lines because you will see that I can once again group these errors together to see the effect. So if I go back to these code words, it should now become clear what happens if I have single qubit X error on 0L. So where did I write down 0L fully? Yeah, here you go. So you see that if X1 occurs, then this becomes 1, 0, 0, 0, 1, 1. If X2 occurs, it becomes 0, 1, 0, 1, 0, 1. And X3 occurs, it becomes 0, 0, 1, 1, 1, 0. So essentially, I have like a mini bit flip code syndrome happening within each set of 3 qubits, right? So this is what I have. 0L, will go. So if it's X1, it becomes 1, 0, 0 plus 0, 1, 1. And then the remaining 2 are the same, right? I'm going to stop writing the 1 over root 2. That's kind of implied, right? If it's X2, then it's 0, 1, 0 plus 1, 0, 1. With the remaining 6 qubits unaffected. And if it's X3, it's 0, 0, 1 plus 1, 1, 0. Again, with the remaining 3 qubits being unaffected. So now this repeats itself for the remaining errors. So I now have, all the other sets I can write down, x4, x5, etc., all the way up to x9. And you will notice that basically I have a set of orthogonal states onto which the single qubit X errors map the 0L state. Again, you can work out that this is similar for the 1L as well, right? So, for example, X9 leaves the first set of 6 qubits unaffected, and the last set has now an error of the form 001 plus 110. So each of these states is distinct. And what is the measurement that you have to do to be able to detect this set of errors? Yes? What is the measurement that one will have to do? What are the measurements rather that one has to do? Are people still around? Has everyone left? Okay, I still see 19 of you. Yeah, I don't hear you, Nilesh. If you can type on the chat.
So it is like Z1, Z2, and all identity kind of measurement.
Exactly. So thank you. So you need basically Z measurements and pairwise Z measurements. So you need, it's the same logic as the 3-bit repetition code, now extended along sets of 3 qubits. So you need pairwise Z measurements. And these pairwise Z measurements are of the form Z1, Z2, Z2, Z3. So when I write down a pair like this, it means Z1 tensor Z2. So it means Z tensor Z tensor identity on the remaining 7 qubits, right? That is what this means. So I have this pair Z1, Z2, Z2, Z3. This will detect the bit flips on the first set of 3 qubits. And then I need to have, Z4, Z5, Z5, Z6. This will detect the bit flips on the next set of 3 qubits. And similarly, I have Z7, Z8, Z8, Z9, and this is going to detect bit flips on the last set of 3 qubits. So that's so far as the X error is concerned. So let me just write this out. So this will, so you can once again form a big syndrome table for this. So this will detect X errors on the first 3 qubits. This pair will detect X errors on second set of 3 qubits. That is the 4, 5, and 6. And this will detect X errors on the last set of 3 qubits. Is this clear? Any questions? Okay, so what? Yeah, go ahead.
Here we're assuming that only X error happens, right? And
no, I'm going to now, yeah, indeed. So I'm now going to look at the Z error. And finally, I'm going to argue that the two sets of measurements actually don't interfere with each other. That is very important, indeed, right? And a formal way of saying that two sets of measurements don't interfere is to say that I performed commuting measurements, right? So that's what I'm going to show. Indeed, that's what the last 10 minutes we're going to do. We are going to look at what about single qubit Z errors. So let's again pretend like only Z errors exist and correct for them. And then we will put them together and show that the two measurements don't affect each other. So what happens? So once again, let me write down something like what I wrote down there. So I have 0L. So now you see, I literally have only 3 sets of syndromes here. So here I actually, how many sets of syndromes did I have here? I have 9 different errors which I've listed out. But if I look at the syndromes, how many do I have? How many syndromes do I have?
6.
Exactly. So I have 6. I have 6 syndrome bits that I get out of this, right? Okay. Now let's go back to Z and ask how many distinct syndromes do I have? So let's go back up to the code words. Yeah. So now, yes, single qubit Z error, Z1 does what? It flips the sign here, right? This relative sign becomes minus for the first set of 3. Z2 does the same. Z3 does the same, right? So now I have Z1, Z2, Z3 all lead to the same errored state, which is 0, 0, 0 minus 1, 1, 1 by root 2, with the remaining 2 sets of 3 qubits being unaffected. Z4, Z5, so maybe I should write this bigger, sorry. So I see, I hope you get the picture now. So this is Z1, Z2, Z3. This is Z4, Z5, Z6. Note that these are commas. These are not happening at the same time. It's not like the syndrome measurement, which is a tensor product of 2 Z operators. This is a single Z operator. The first set of 3 remains unaffected. So I should put the root 2 here. And the last set of 3 remains unaffected. The middle set gets a relative phase change. It is important to note that not only is this pair mutually orthogonal, these two states, right? This one and this one, which I just wrote down, they are mutually orthogonal. But what is important is that they are orthogonal also to the 1L. Because remember, the 1L has a minus sign in all the 3. Okay, so it's important to be able to distinguish these states also from the 1L state. So not only is this set of 3 orthogonal to each other, they are also orthogonal to the 1L state. So 1 minus 1, 1, 1. Okay. So once again, all mutually orthogonal and orthogonal to one L as well. And this is important. Okay. So not only are these 3 states mutually orthogonal, they are also orthogonal to the other logical state, which is a 1L state. Similarly, you can figure out that with 1L, which was like minus, minus, minus was the phase structure, that becomes either plus, minus, minus, or minus, plus, plus, or minus, minus, plus, right? I'm just talking about the relative sign, right? Because that is where the change is happening, right? So it's like I can simply look at this sign and write that down, right? That is essentially my syndrome now. So formally, how does this, what is the syndrome measurement in this case? So these are now, so this is similar. So similarly for 1L, okay? So they can all be detected. So this set of errors, which is Z1, Z2, etc., Z9 can be detected by X measurements. Now, what are the kind of X measurements that I need to do? I now need to do, so if you realize, right, the structure of this code was what? Underlying it, like I said, is a 3-qubit phase flip code. So if I simply had a single qubit phase flip code, what is the X syndrome that I would do? I would do X1, X2 and X2, X3, right? For the single qubit. Sorry, I'll just write this as the standard. So recall that for the 3-qubit phase flip code, these were the code words, right? Plus, 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 and minus, minus, minus. The syndrome measurements were of the form X1, X2, and X2, X3. But now you have concatenated this. Now each of this has a set of 3 qubits. Each of this has a set of 3 qubits, and each of this has a set of 3 qubits. So what is the X measurement that you will do now? Any ideas?
X1, X2, X3, X4, X5, X6, and then
Indeed.
X9.
Exactly. Very good. So now that you have concatenated this with a bit flip code, so I'll just put this in a bracket. So this is just for you to understand where this is coming from. So now the X syndrome measurements are a 6-qubit collective measurement of this form, X1 to X6, because you see, this is like now a pairwise X measurement, right? This will tell me whether the relative phase of the first 3 and the second 3 have flipped or not. It's like a pairwise check, right, of these relative phases for the first 2 sets of qubits. Similarly, we then have to do another check, which is X4, X5, X6, X7, X8, X9. So you now have 2 sets of, so this will now give me 2 syndrome bits. Okay. Remember that these are all collective measurements, right? So these are all collective measurements. It's not like I'm taking 6 classical bit values out here. I'm going to attach a single ancilla to 6 data qubits, to 6 encoded qubits. Similarly, here I'm going to attach a single ancilla to 6 encoded qubits. Here it's the first 6 and here is the second 6. And these are now collective measurements. So in all, I have a total of 8 syndrome bits. 6 of them coming from Z and 2 of them coming from X. Now comes the question that Sriram asked. How do we know? So as far as the Z syndrome is concerned, we pretended like there was no X error. I'm sorry, there was no Z error. And as far as the X syndromes were concerned, we pretended like there is no X error. I'm saying it the other way around. Yeah. So as far as the X syndromes are concerned, we pretended like there's no X error. And as far as the Z syndrome is concerned, we pretended like there's no Z error. So now how do we reconcile this? The point, as I said, is to show that. So if I can now show that this, so there's a total of 8 syndrome bits, which means a total of 8 measurements, right? 8 collective measurements of the encoded qubits. The question essentially is, can these 8 measurements be performed simultaneously or not? Okay, so we need to perform 8 collective measurements on the qubits. And I will stop with the statement that these 8 measurements can be performed simultaneously Why? Why can these 8 measurements be performed simultaneously? Yeah. Okay, what do they need to do in order for us to be able to perform them simultaneously without one interfering with the outcome of the other?
Having ancillary qubits, like extra ancillary qubits.
You see, even the ancilla is just a tool to perform the measurement, right? If fundamentally I have measurements which are going to affect, so then, the question will become, is there some sequential order in which you have to perform them? Suppose I perform the Z measurements first and then the X measurements, and or if I reverse the order, is that going to change? That shouldn't happen, ideally, right? That's what I mean by saying that they can be simultaneously measured. So the ancilla is just a tool to make sure that the encoded qubits are not disturbed. That is true. But even with that, I can only perform compatible measurements. I cannot perform incompatible measurements, because then the sequence in which I perform the measurement will matter. And I've already given you enough clues. The sequence matters means what? Whether Z times X is the same as X times Z. Well, it is not. But I now have tensor products of Z's and X's such that they all commute. Exactly. Good. So they all commute. So the point is, when I have something like X1 tensor, X2 tensor, etc., X6, and I look at Z1 tensor, Z2, well, of course, they commute. Similarly, Z2, Z3, etc., Z8, Z9. So these pairwise Zs, all of them commute with these 6-qubit X measurements, right? So I essentially have a set of 8 commuting measurements which detects this set of single qubit X errors and single qubit Z errors. And the fact that they all commute means that these measurements can be performed simultaneously, which means that, for example, the order doesn't matter. Whether I do the X syndrome first or the Z syndrome first doesn't matter. And so what this means is that I can independently detect and correct for single qubit X and Z errors. So that is single qubit, bit flip, and phase flip errors. So let me stop here. I think I've exceeded time today. I'm sorry about that, but I just wanted to complete the argument. Questions?
Ma'am, how this two syndrome bits with using X measurement is found? I mean,
Sorry, Nilesh, you're breaking off a lot.
sorry, how can we measure these two syndrome bits, last two syndrome bits?
The X tensor 6 and
Yeah.
Well, I showed you the single X measurement here, right? With a single ancilla, sorry, with one data qubit. Where was that? Oops. Yeah. So you simply now have to imagine. So let me draw that at the end. Sorry. So let me just show you one of these measurements. Those who want to leave can leave. I'll just answer this question by drawing a circuit. So let's say we want to explicitly show a circuit for this measurement. Remember that I now have 9 data qubits. And I'm going to have a single ancilla qubit. The single ancilla qubit is going to be initialized in the plus state. And then I'm going to do a whole bunch of C naughts. Sorry. So yeah, my tablet is really come of age in the pandemic. And I think any more online classes, I hope it lasts this semester, at least. Okay. Right. So now I have this. Oops. This. Okay. So this is x1, x2, x3. This is x4, x5, x6.
Okay. So these data qubits are in X spaces. That means, yeah. Okay.
This is well, the point is, you see, even if my data qubits, I write them in my 0-1 basis, the point is to visualize them in the plus-minus basis, right? And then the same logic goes through. So yeah, you can work this out explicitly, and if you still have trouble, I can try to work it out explicitly. But it's just a matter of writing it down and seeing that this set of 6 C naughts is going to extract out the syndrome for, and of course, now you have to measure basis. The key is to initialize the ancilla in the plus state. Okay, that is the key part. And then whether the ancilla gets flipped or not in the X basis is what is going to reveal whether the relative phase of these 3 qubits flipped with respect to these 3 qubits. Okay.
Yeah, ma'am. Yeah, thank you.
Yeah, sure.
Ma'am, I have a question. So, like here we assume that phase flip and bit flip will happen independently.
Yeah.
So in that case, I mean, like taking both the, I mean, the probability as P for both of them. So like both happening, well, like we designed a circuit for both of them happening at the same time, right? Like in a sense, like
So the
even
point is that the same, yeah, go ahead.
like in a sense, like even if both happens, we can still detect and correct the circuit.
Yes,
With this particular code.
Yeah,
Right.
yeah,
So
yeah.
but then like there's an equal probability that like 2x can happen. I mean like 2 bit flips can happen, right? Because like taking pp as the probability for x and z, so that both happening is p square, which is same as like x happening twice.
That's a very good question. Indeed, if I have x and z happening on the same qubit, that comes with a weight p squared, right?
Correct.
But the point is, I can therefore, as far as this code is concerned, it looks like there are certain order p squared errors which I can correct, right? And those are the independent x and z order p squared, because the x and z syndromes are different. So there is no scope for confusion between an order px and an order pz, right? But an order px and an order px on a different qubit, there will be scope for confusion. So actually, it turns out, if you do the analysis, and I will do that in one of the later lectures, I'll just point this out. The 9-qubit code can actually detect, over and above single qubit X, it can also detect some 2-qubit X errors. Okay? Because there is now a lot of room, right? You have gone to a 9-qubit Hilbert space. So it turns out that there is actually scope for detecting some of the 2-qubit X errors as well, or some of the 2-qubit Z errors. Okay. For example, you can see that if I do, oops. You see, it doesn't have to just be Z1, Z2, Z2, Z3, right? I can also compare, I mean, independently, I can have an X error on the first set of 3 and an X error in the second set of 3. That is 2 X errors, right? And those 2 will be detected by this code. You understand? So it depends on the location now. Not all 2-qubit X errors can be detected, but some 2-qubit X errors can be detected, depending on where they occur, which set of 3. In the same set of 3, if I have 2 X errors, I cannot differentiate that from the single qubit X errors. But if I have an X error in the first set of 3 and another X error in the second set of 3, I can indeed detect this. So that's why this code actually has more room. However, it cannot correct for all 2-qubit X errors, right? Like I said, if both the X errors were to occur in the first set of 3, then I can't correct for it. So that's why I cannot claim that this code can correct for all possible 2-qubit errors, but it can certainly correct for all possible single qubit errors. Right?
Yes, ma'am. Got it. Yes.
Yeah. Any further questions? Okay, so next week we'll look at how to identify such kind of code spaces, right? This was something that Shor developed based on the idea of the classical repetition code and then extending it to phase flip and concatenating them. So can one develop a method to identifying codes for specific noise channels? So we'll do that next week. See you all on Monday then.